The synthesis of superheavy elements serves as a rigorous stress test for the standard model of particle physics. At the extreme edge of this domain is Moscovium, designated by atomic number 115. Synthesizing this element requires overcoming immense Coulombic repulsion. In highly advanced cyclotron accelerators, researchers fire a beam of stable calcium-48 ions into a target of americium-243. The fusion cross-sections are so astronomically low that a successful reaction yields only a few observable atoms per experimental run. This 3D visualization shows the theoretical architecture of the Moscovium-299 nucleus. To achieve cohesion, the structure relies on a specific configuration of 115 protons and an idealized closed neutron shell containing 184 neutrons. However, in actual laboratory synthesis, creating that ideal neutron count is currently impossible. The actual neutron-to-proton ratio for synthesized Moscovium sits at just 1.60. This severe neutron deficiency stretches the binding energy to its absolute limit, causing the nucleus to violently decay via alpha emission in mere milliseconds. This chart maps nuclear stability across known and theoretical elements. The theoretical isotope Moscovium-299 sits near a predicted peak known as the island of stability, where specific closed nuclear shells might stabilize the element long enough to exhibit entirely different physical properties. Because orthodox nuclear chemistry dictates that current isotopes of element 115 are characterized by profound instability, evaluating its potential for macroscopic engineering requires analyzing how a stabilized version of this superheavy nucleus interacts with non-standard models of the quantum vacuum. In 1989, a highly complex parallel discourse emerged from Robert Lazar, who outlined classified operations regarding the reverse engineering of anomalous aerospace architectures. The core postulate of Lazar's narrative was precise. A highly stable isotope of element 115 serves as the physical substrate required to generate localized spacetime distortions, allowing for macroscopic gravity modification. This creates an immediate paradox within classical physics. The strong nuclear force binding a nucleus operates strictly within femtometer ranges. Standard chromodynamics states that this force is exponentially bounded and cannot permeate past the nucleus to project a macroscopic gravitational field. Bridging the gap between a femtometer-scale nucleus and a macroscopic gravity wave requires replacing standard general relativity with alternative frameworks. Theorists deploy relativistic atomic physics and hydrodynamic models of spacetime to explain how superheavy mass mathematically interfaces with the quantum vacuum. Scaling the strong nuclear force up from femtometers to the size of a spacecraft requires a total re-evaluation of how mass-energy density influences the vacuum around it. By discarding the surrounding lore and analyzing the established physics of relativistic electron clouds alongside pre-geometric fluid dynamics, we can derive the precise mathematical and physical requirements for metric engineering. As atomic numbers increase beyond Z equals 100, the extreme positive charge of the nucleus exerts immense electrostatic pull. To avoid collapsing directly into the nucleus, the electrons residing in the innermost shells of Moscovium must orbit at roughly 84% the speed of light. This formula is the Dirac equation, a formalized method in relativistic quantum mechanics used to calculate the behavior of many electron fields when classical Newtonian mechanics completely fail. This comparison model illustrates a primary consequence of the Dirac equation. At extreme velocities, effective mass increases, causing severe spatial contraction. By drawing core electrons closer to the center, this creates an intense shielding effect against the 115 protons. This schematic demonstrates spin-orbit coupling. The magnetic field from the rapid orbit interacts violently with the electron's spin, breaking degeneracy. The 7p subshell is torn into two distinct states, a stabilized state for 2 electrons and a destabilized state holding a solitary valence electron. This massive energy gap creates an inert pair effect. The stabilized electrons behave as closed shells, rendering them highly contracted and almost entirely chemically unreactive. From a geometric perspective, these extreme relativistic effects surround the Moscovium nucleus with an ultra-dense, nearly impenetrable boundary layer of electrons. This contracted core is the physical surface required to interface with the ambient quantum vacuum. Traditional general relativity models gravity as the geometric curvature of a four-dimensional manifold. This framework demands planetary-scale masses to warp spacetime, making the concept of a compact gravity reactor theoretically impossible under standard Einsteinian physics. To resolve this energy crisis, engineers utilized the polarizable vacuum, or PV theory, originally proposed by Robert Dicke. The core tenet of PV theory relies on an optical mechanical analogy. It states that localized mass does not bend an empty void. Instead, it physically alters the electric permittivity and magnetic permeability of a flat spacetime vacuum. These combined properties are represented by a single scalar parameter, the dielectric constant of the vacuum. Modifying this constant directly alters the lengths of rulers and the ticking of clocks, perfectly mimicking the effects of curved spacetime without requiring planetary mass. To explain how a superheavy element modifies this dielectric constant, physicists reference the Quantum Modified General Relativity framework, redefining the physical structure of empty space. Under this model, the vacuum is not an empty, rigid geometry. It is a dense, manipulable hydrodynamic superfluid that self-organizes into a stable topological lattice. Replacing a rigid geometric void with a compressible superfluid lattice is the absolute prerequisite for metric engineering. It dictates that matter acts dynamically as a compressor that strains the local vacuum. The degree to which an atomic nucleus compresses this vacuum fluid is mathematically governed by the linear density law. This law exposes a profound mathematical divergence in nuclear scaling. As atoms get heavier, their physical volume scales in a slow linear progression. However, the Vorton interaction energy, the fluid equivalent of the strong nuclear force, scales with the square of the mass. This line chart compares these two variables. Because energy density is the ratio of energy to volume, the squared scaling forces the local interaction energy density to spike exponentially as you move up the periodic table. For lighter elements like iron or lead, the energy density remains too low. They lack the physical mass required to overcome the topological stiffness of a vacuum lattice, meaning the spacetime metric remains entirely flat. But as mass approaches atomic number 115, the energy density sits nearly 6 times higher than that of iron. At an atomic mass of 299, Moscovium reaches the exact saturation limit of the vacuum fluid itself. This extreme density spike forces the superfluid vacuum to bulge outward. The superdense electron core is compressed directly against this boundary layer, creating a localized macroscopic deformation of spacetime known as a metric hill. This blueprint details a hypothesized hypercompact cyclotron reactor. Its architecture is specifically designed to destabilize the metric hill surrounding the Moscovium nucleus. The system operates by accelerating a high-energy stream of protons and firing them directly at the stabilized Moscovium target wedge. Upon absorption of a proton, the element 115 nucleus undergoes an instantaneous nuclear transmutation. It briefly becomes livermorium 300, a critically unstable element. Shattering the stable density threshold triggers a violent, pulse-driven discharge of the highly compressed vacuum lattice. This discharge is evaluated through the dual-sheet model, which posits that spacetime consists of separate spatial layers, sheet A and sheet B. Under this model, the extreme energy pulse disrupts the vacuum lattice so intensely that it creates chiral interactions, forming a momentary bridge between these two spatial sheets. This cross-sheet bridging creates a chiral imbalance, providing a physical mechanism for the spontaneous generation of antimatter directly from the secondary sheet. This provides a high-density energy source without the requirement for volatile onboard storage. Ultimately, these violent chiral pulses actively force the local effective gravitational constant below zero. By inducing a negative value, the system creates the repulsive force necessary for inertial reduction and lift. Controlling this reaction requires exact frequency tuning. The electrogravimagnetic construct achieves this by reinterpreting mass not as a solid lump of matter, but as a localized density of wave function energy. By decomposing the mass energy of the nucleus into spectral frequency modes using quantized Fourier harmonics, researchers can calculate a resonant signature for the 115 nucleus, exactly 11.4 GHz. This cross-section diagram illustrates the physical architecture required to channel a wave oscillating at 11.4 GHz. Because this frequency sits firmly within the standard microwave spectrum, the craft relies on known microwave engineering principles. The internal layout utilizes standard beryllium-copper waveguide pathways to capture, phase shift, and directionally project the 11.4 GHz signal down to the emitter array. This schematic visualizes the resulting macroscopic phenomenon. By harmonically coupling the projected microwave radiation with the intrinsic metric hill of the reactor, the system generates a targeted, high-energy gravitational distortion field. While empirical proof of a stable element 115 isotope remains absent, synthesizing relativistic quantum mechanics with hydrodynamic vacuum models explains why gravity modification is fundamentally a density problem. Ultimately, this advanced framework links the microscopic properties of the nucleus to the mechanics of macroscopic gravitational control.